to talk to this group. I didn't realize you made a big announcement and did such a good job to send this to a lot of people, and I got some feedback, and so I got this notice, and then looking forward to this presentation. So to add a little bit more pressure on me, how can I deliver this talk? But I will do my best. Again, thank you for the invitation.
Sure, my pleasure.
So just to fit to the theme of the bigger data, so the talk is about how can we get data and how can we use data and also convert data into something is actionable. So it's how to make sense of data. That's kind of the theme of the talk today. So it covers kind of several topics, and then I'm condensing the things into a few slides, and hopefully I can get a point across. But also want to emphasize this is the work done at the P&L. I led or leading or I'm involved. So it's not all done by myself. I have to make that caveat before I get into the slides. And I maybe some of you, either P&L colleagues or ex-P&L colleagues, maybe in the audience, and for some of the topics you may know more about it. So maybe I will probably rely on you to answer questions later on. So with that said, let me jump into these slides for the next probably half an hour or so, and then I would really like to have a conversation on how we all can come together and then deal with these big data issues in the power grid area. And as many of you probably know, when we say big data, the big is not really only mean volume. The different things when data become big. Volume is just one of the things we have to look at. And here I put some attributes here. You see, volume is one of the four things usually the big data community talk about. Of course, we do have a bigger volume. If you look at the phasor measurements over the last maybe decade or so, I was involved in this phasor measurement effort as early as 2003. So that was probably 15 years ago. At that time, there was something called a NASB. Actually, they were called EIPP at the beginning. It's the Eastern Interconnection Phasor project, and now become NASB, and many of you probably already involved. So over the last 15 years, it's growing a lot. From at that time, only probably less than 50 PMUs in North America, come to today about maybe 2,000 of them. So you can see the growth is significant. And also back then, maybe it was only 20 people involved in the meetings, and now every year NASB has a working group meetings in anywhere between 200, 300, 400 people involved in those meetings. So you can see also the interest also growing a lot over the years. But then again, volume is one thing, and PMU data is higher speed, as you all know, from once every few seconds to 30 to 120 samples per second. So it's much faster, and how can we deal with that? It's also become a challenge. Particularly, we want data because we want to know what's going on in the system. But if your processing time is not catching up, then even get more data, but doesn't mean we get more knowledge of the system. So that's a challenge regarding the speed and also the time you have for data processing and analysis. And of course, PMU offer a lot of more data in addition to voltage and current, also offer phase angle and other things being included. And with the kind of data, we can see more details of the system, like oscillations. We used to not be able to see it from scatter measurement, and now we can see it in the PMU measurement. So all these things kind of play a major role, and then many people involved in either one or more of these aspects in the research for the last couple of decades. So that's one trend. And another trend about the data is smart meters. So this is one example, the work P&L led. It's a Pacific Northwest micro demo project. That was over a couple years ago, but was lasting for 3 or 4 years. Installed thousands of smart meters in the Pacific Northwest states. Again, they get you more data, right? So terabyte data, just in a smart meter area, and talk about if you have a smart meter for every home in the United States, you would have 200 million smart meters, because there were about 200 million households in the United States. So that again is another significant bigger data aspect. And not only just that, I think we're probably familiar with phasor measurement of smart meters, many of you, but the other data which probably less talked about, but they can be very important for power grid. So examples. Another effort at the PNL, which I'm not involved, but I know about it, is it's called ARM. They collect a lot of data for weather and climate. So they have a sensors just to measure the atmospheric properties, like the wind speed, temperature at different height. They have the sensor, like this is one picture of this kind of sensor, but they have sensors at different height and to measure that. So it's really three-dimensional sensor system to get all the kind of data. And I think it can be useful. For example, you can use this kind of data to do weather forecast or prediction, and also managing temperature trend, and which can affect the power grid load. So that can be also important for us to look into. Actually, we are using some of the data now in one of the projects to look at the wind distribution, and how can we take that into power grid analysis with the good wind model. So that's one example. And then, of course, in power grid, we have a lot of market data, business data, and they can also be very important for the grid. And the cyber information, they are efforts collecting cyber communication information, like a cyber log, cyber traffic, and so on. Again, given the power grid, they rely on data so much, and cyber issues can have a major impact on the grid. Last but not least, there's a lot that we simulate. We're very good at the simulation, as the power engineers, because we cannot do real experiments, so we do a lot of simulation to understand the system behaviors and so on. So how can we really get the knowledge out of this large amount of simulation? Here's again a couple of examples. Just simple as there's a continuous analysis application in power grid. If you analyze those large number of scenarios, you end up with a lot of data as a result of this simulation analysis. Using Western Power Grid WAG as an example, each power flow result file is about 0.5 megabytes. If you have thousands and 100,000 millions of those files, then you could end up with a lot of data. By the way, since the chair mentioned I was working on the parallel computing work as well, so with that, I guess we can do things or run the simulation faster. But one challenge we will end to have is we have more data, because you run it faster means you can run more cases in a short time frame. Like I show in this picture, that means you get more simulated data to deal with. So this all adds to the big challenge of bigger data in the power grid area. Also put this into the context of how power grid data compared to other domains. I'm trying to make a picture to show the scale. So the top are some examples of other domains and how much data they have to deal with. For example, there's at the P&L, there is efforts collecting cyber data, which is the traffic information on the internet is 35 terabytes a day. And then the second one is EMSO. It's environmental molecular research. They have experiment like those big equipment that measure the spectrum information of the materials, for example. They can end up with terabyte or petabyte data volume, and they have to analyze. This is the Bell 2 experiment. It's a physics experiment. It can have anywhere, hundreds of petabytes data as well for from those experiments and then have to analyze. So those other domains that have data from terabytes, petabyte kind of scale. Now power grid area, we are catching up. We're not quite at that 100 petabyte level, but over the years, as you see at the bottom of the picture, if in old days, we don't talk about scatter measurement and the data estimation. It's only at the gigabyte level. You talk about PMUs, 45 PMUs one day is again tens of gigabytes. You get more and more PMUs in the system. If you have a PMUs at everywhere in the power grid at transmission level, it will be petabyte per year. And compared to AT&T, global data is petabyte a day. So we are getting to the level of these bigger data challenges. Even our volume is not compared yet to those largest kind of data challenges in other domains. But one thing I want to point out is we do have these real-time issues. We are kind of unique compared to other domains. For example, those physics experiments, they run the data and they can run analysis as long as necessary. But for power grid, as I mentioned, if you have PMU coming in, you have to analyze the data within a very short time frame. So that's kind of unique for us. So that become a challenge. Now, given that, how would we be able to deal with it? Given the high speed, high volume, particularly for the grid. So one thing we did is really to figure out how can we even get the data into the location you want it to have. It's data ingestion and the retrieval curation process. So ingestion means you have data coming from the network, and then at the central location, the control center or some other places, you have database. You want to at least receive the data and put it into the database. Now imagine if your ingestion process takes too long, the data like a water flow keep coming, and then it easily overflow, buffer, and then you end up losing data. So that's of course not good. So we did some work here. Particularly, we compared it with MySQL mechanism. This is one of the many things that people are doing, and the MySQL is just one of the methods. We use that because it's very popular in many of the databases. For example, PyDatabase uses some kind of MySQL mechanism to manage this ingestion process. It takes quite time, 10,000 milliseconds, as you show in this green curve. So at the PNL, we did some work. We did develop this data ingestion process at a lower level, more hardware-oriented approach. We can reduce the time by thousands of times. At the bottom red curve, we can see for both ingestion and retrieval, with many of the records, as you 200,000 records can be reduced to a few milliseconds. So that's significant compared to what we need to do for power grid. So that's one piece of work. And another piece of work is data curation. Curation here means data coming in with noise, with outliers, and missing data, and so on. So we have to fix those things. So that's part of curation. And another part of curation is we do some kind of initial data analysis and figure out what is special of the data at any given moment. Maybe there's some event happen, we say, okay, here's something interesting, we should label it. So we did all that as part of curation. And then in that case, we're able to deal with a very large number of bytes in the database in a very efficient way. And here the picture shows there's a big computer, has a 10,000 core computer at the PNL, and use Hydromap and R language to deal with that. So that's how we be able to improve the performance of data curation. So that is how we think the challenge would be just from the front end. how to get data into the places you want it to be. So that's just first step, right? Now, once you get data into the place you want to be, save it and then store it in the database. Next step, naturally, then becomes how can you get data to the applications? Either it's the status estimation, either is some kind of alarm processing and visualization, and how can you get data into those different different applications? So here is mostly what has been done today. On the right hand side, you have many different Power Grid applications that use data. On the left hand side, you have all kinds of data input. It can be PMU, can be smart meters, can be your model data, or can be configuration information. So the data need to be linked to the applications. Today, mostly is one-to-one connection, which means if my application, for example, status estimation, I need scalar measurement or maybe phasor measurement, I will have to have my own link or mechanism linked to the database and then retrieve the data and then bring to my application and run my computation. If I have another application, like a LAN process, then there's another connection to the data and so on. So you can imagine if you have so many applications and a lot of data sources, then you end up have a lot of these one-to-one connections, and then quickly become end-to-end connections, and it's very hard to manage. And it's prone to problems. So, and also not efficient, of course. So that is a challenge, and we saw. And with that, we say, what if we have something between, some kind of middleware to manage all this data coming into the system, whether they come in, different speed, different volume, and different formats. We have this thing in between called Gauss to be able to just take data in and then pass the data or packets and then put kind of format the application would be able to use. And applications then don't have to have a direct link to the data sets, and only need to have an interface to Gauss middleware, and the data will be ready. And the application even don't have to worry about what kind of format come in with the data. Even for example, PMU data can come in different problems or different time instance and so on, and then the alignment, everything all being handled by Gauss, and then we don't need to burden the applications. So that's the way we thought good efficiency and also better management of the data. And then here's a little bit more better picture about how this Gauss would work. At the bottom, you have all different kind of data sources. On the top, you have applications, different languages or different purposes. Again, the goal is to separate application and data. Application don't have to worry about the details on the data side. For example, just use myself as an example. I'm more in the area of modeling, simulation, control. I may be, have more knowledge about how to build models, how to run the simulation, but I may not know as much about protocols, databases, and so on. So in this case, we would rely on those experts. They can develop those database side of things, protocol communication side of things, and then I, as a developer of application, don't have to worry about it. So that is the goal of Gauss. And there's a link here. Both its open source software codes as well as some documentation you can look at. So that's Gauss. Any questions so far? Or should I wait until the end?
Oh, I guess, yeah, wait until. Yeah,
okay.
In the past tense, but yeah, so feel free to go ahead. I think it's good.
Okay, thank you, Yan. And then continue on. So another challenge I want to also bring out is in the power grid, we have all kinds of measurement data and also simulation data. I think there's a lot of opportunities to leverage the knowledge buried in those different kind of data and to make a decision with those kind of input. So here, this picture is very messy, but the main point is that you have a lot of data input at the bottom, left side at the bottom, you put it into the system. And then the middle part is how can you reason based on the multiple kind of data input, and then eventually at the right hand side, you would have output to operators or any other users to say, okay, here's the best information decision based on all this kind of data combined. Versus you make decisions on a single kind of data. Let me give you maybe a quick simple example. For example, if you observe on your screen, your voltage dropped to 0 from 500 kV. The alarm went off, and without any other information, of course, everyone would think, oh, maybe that's outage somewhere. So maybe short circuit. That's why the voltage dropped to 0. Now that may or may not be true, but if you don't have any other information, then that's probably the only thing you can reason about. But if you would have more information, for example, cyber information, the cyber system information shows, oh, don't worry, that data just been manipulated by someone, and then it's not true physical phenomenon, it's just a data problem. And then you would make a whole different kind of decision. Okay, now you don't have to worry about the real system. You will then worry about your cyber system, and then what's going on with the cyber side, and find out how this data being manipulated, and then what should be the true value, and then you can deal with that situation in real time. So this is just a simple example. Combine real data and the cyber data, then you'll be able to have a much better decision making and the reasoning in that situation. So here the picture shows, of course, a much complex situation. Yeah, you will come in, you have a load of broadcast error information, you have alarm information, you have a wind information, and your EMS system may give you a lot of alarms, and then beeping or flashing and so on. And then the key part is we can take all that different kind of information as input and reason about the system and make the best decision. So that's the purpose of this kind of multi-domain data reasoning. Now we did some work on this, but I don't think we solved all the problems. I think there's still a lot more to be done. Particularly, I guess today, just to link to today's buzzword in the machine learning or artificial intelligence, I think there's a lot of things that can be done using machine learning and or artificial intelligence to be able to deal with data and to be able to make better decisions. So many of you are doing this, including some of you in the audience. So that's really a big challenge, but also a big opportunity. So how can we deal with data in this case? So this is a challenge in how to leverage multi-domain data to make a good decision. Now here's another challenge, the speed challenge. As I mentioned earlier, I'm showing you the result we have got for one of the applications using data. It's called dynamic state estimation. Just quickly about this particular application. Dynamic state estimation is to use phasor measurement and also the differential equations of the power grid, so we can estimate the dynamic states versus traditionally we estimate just the voltage and current at the buses. We can really estimate the generation speed and angles and other dynamic states in the power grid. So that's dynamic state estimation method. We started this work back in probably 2005, 2006, and now become a very popular topic now, and IEEE has a task force on this particular topic. So that's an application. But what I want to show today is just the challenge regarding speed. Think about state estimation. It's a real-time application. your PMU data coming every 30 milliseconds. That means whatever mathematics or computation you need to do with the data, with the physical measurements, will have to be finished within 30 milliseconds. Anything slower than that, then you are falling behind. And that means you cannot finish computation before the next set of data coming in, and then that is not going to be useful, and end up losing data or losing the view of the power grid. So here the bottom picture shows where we were last year regarding this application. So look at the x-axis is a log scale. 30 milliseconds is labeled. This is a vertical line. So anything to the right side means it's done less than 30 milliseconds. That's good. Anything to the left side of the vertical line is taking longer than 30 milliseconds. Then that's too slow. So over the years, we've done the work, and then for like a 1,000-bar system, we were able to finish that within 30 milliseconds, no problem. Of course, the paracomputing being used here, by the way. Then for the web size system, which is 16,000 buses, we were very close. We were probably at 300 or less milliseconds last year. So not yet at the 30 milliseconds. So that's a challenge. And how can we continue to develop application and the computing and be able to catch up with the speed? So this is one example to show the speed requirement regarding the power grid big data challenge. Now, I want to say this is just an example. There's some other examples as well, which would have time requirements, and then have to finish whatever within 30 milliseconds, depends on how you use the data. So I think that's a challenge as well. But it's not done. There's more challenges. We also did work in just on the data itself. The reason why we did this is that for a lot of the data-based application in the power grid, we usually assume the data has a Gaussian noise or Gaussian errors involved in the data, including the application I just showed for the dynamic estimation. That is a common filter-based approach, and the common filter require the input of the measurement covariance. We assume it's Gaussian, so that's what we did. Now, there has always been assumption over the many decades. I haven't seen any solid evidence to show the power grid measurement data is truly Gaussian. So that's something we realized, and then we went back and then let's take a look and see what kind of noise property is in this power grid data. So we did an example for the PMU data. So the left-hand side picture is actual PMU data noise. The right-hand side is the noise property. And the p-value, many of you are familiar with statistics. The p-value, if it's larger than 5%, then it's likely to be Gaussian. If it's it's very likely to be non-Gaussian. And here is 0. So it's very unlikely the power grid measurement has a Gaussian noise. So now that's interesting observation, and we had a paper published just on this Gaussian property analysis and on attribution sections. So that's more details in there. But then I think from application perspective, really need to think about what's the implication of non-Gaussian noise to the applications. Maybe for some applications it doesn't matter, but for many other applications it does matter. Particularly, say again, use the example of the dynamic estimation. We did some initial work and then to compare with or without the Gaussian assumptions, what kind of difference it might be. The difference could be big enough for us to care about. In that case, then we may need to figure out how can we deal with this kind of data with non-Gaussian noise, we can do things like a particle filter, which does not need a Gaussian assumption, but it takes a lot of more time for the computation. Or there's something called a Gaussian mixture methods, which basically means we can decouple this distribution function, which is non-Gaussian, into multiple Gaussian summations. It's kind of like a free analysis, but here it's decouple the PDF function, the probability density function of this noise. There's a lot of things can be done, but I think that this is still a challenge to be solved for the power grid applications. So that's a lot of things we need to look at. I guess so far I talk about how big a data is. Big is not just the volume. Big means other things too, like speed. And then how can we get it into the database and be able to ingest and retrieve and curate the data, and how to use the data to support analysis like a Gauss, so we can easily manage the kind of data interactions, and also challenges regarding the speed, regarding mathematics, like this non-Gaussian problem. So there's a lot of things, I guess, need to be done. I guess today I'm provide you more questions than answers, I guess. But there's more questions I would have to say. So again, assuming you can take data in and support your application, and then at the end of the application, usually you generate data. So data does not really give you anything useful. So it has to be knowledge, and how to convert data to knowledge is another big challenge. And the things can be done. For example, you can do visualization to deal with that challenge. And here's some work actually led by Yu Su Chen at the PNL for BPA. It's how to visualize the hydro information. And today, which is a very common way to show the data to the users, is just to make a table, like the top picture shows. That's actually from the real application tool by a vendor used by BPA and others today. It's to show this hydro information along the Columbia River. If you pay enough attention, you can see the 3-letter acronyms. Each of them is a dam along Columbia River. And there's information about generation, about how much power it generates, and temperature of the water, and so on. It's a lot of numbers. Now, if you look at this picture, it's very difficult for any user to quickly know what's going on in the system. So not efficient. So Yusu and the team come in and say, let's convert that table into a picture, a more user-friendly picture, like the one shown at the bottom on the slide. So in this case, then all the same information become the colors and the lines and the bars and the picture, and they have meaning. So let me tell you what we did here. So of course the blue or the middle part that shows the river, that's Columbia. Each bar, the white bar, is a dam, and then there's a name on the left hand side corresponding to these dams. Like the first one is Grand Coulee. That's the largest hydro dam along the river. And the second one is Chief Joseph, as another one, a big one as well. So and so on. And then the blue shows Columbia River. Then there's a little bit of yellowish color on the right hand side. There's another river getting into Columbia. It's called Snake River. There's also dams on the Snake River as well. And then the color shows the temperature of the water. Now, why is that important? Because temperature would affect salmon migration, and that's a big environmental concern in Northwest, particularly for this the Columbia River. So that's why temperature is important, and then the water needs to be managed also for the purpose to facilitate salmon migration. So that's why lot of information need to be looked at the same time on the picture, so you can operate and optimize those hydro dams. And then more information, the bar height on the left hand side shows the speed of the water, and so then you can convert, in this case, the table on the top into a picture. It can easily understood by a user. So that's one example. How can we actually managing this particular aspect of converting the data into knowledge? And here's another way to convert data into knowledge. It's the wind visualization. It's called glyph technology. So again, our Power BI team up with our visualization team, and then to figure out how can we have a really compact visualization, but comprehensive, to show all the information necessary for operators. So that's end up to be this picture, and then look at this. Is basically it's the wind socks picture, and then all the attributes of the wind socks has some information about the data. So for example, like the length of the tail is the speed of the wind. The orientation of the tail is the wind directions, and the head, the size shows how much wind generation might be for the particular wind farm, and so on. So that's again another way to show how the kind of information can be visualized in a way it's easily understood, rather than imagine if a table shows all the same information but it's hard to understand quickly. So another way. And this is one more picture about the hydro generation. It's 24-hour picture to show the hydro trend, and this is another way to look at the different hydro dam and how much they generate over time, so you can get a feel of how the generation go up and down over a day time period. Of course, you can make it to be any time period. So again, visualization can be a major part of the solution to convert data into knowledge. But I also want to emphasize, visualization is not just about the beautiful pictures. Behind the pictures, there's a lot of analytics being performed, like a data correlation and so on. So it's really it's a visual analytics is being done here, not just beautiful pictures. So that's again involve a lot of research and behind the picture and how to best show the information. So with all that, I have a couple more slides I want to show you, which is about data management. This is a data repository we develop and host at the P&L. Is how to make data available to users. And here it's quite complex. Let me show you what we have done. So the top, there's a data repository, and there's the web portal. The portal is the interface to the user, and on the right hand side is the user space, and you can log into the web portal, and then you can get the data from database. And also the bottom is some tools you can use, including
Larry.
Yeah.
Sorry. Yeah, I find the slide is not changing on my screen. For example, I'm still looking at your multi-dimensional wind visualization. So is this the right one you want to talk?
No, it's not. It's not. Thank you for letting me know. Let me. I don't know why. Let me reshare and then see what happens.
Yeah, if you can, maybe you share only the slide. If you share the whole computer screen, we can see more.
I am sharing the whole computer screen.
Okay. Yeah, now we see something different.
This is ARPA-E. This ARPA-E thing on the picture.
Yeah, it is
okay.
There.
Okay. So that's sorry about it. I don't know why. Maybe let me go back. Okay. So you were seeing this picture,
right? Yeah.
Okay. And then I was talking about this picture about the hydro trend. 24 hours.
This one.
Okay, sorry about that.
No problem.
And then I was talking about this data repository and how data can be managed in a way it's easy for user to access and to use. So this data repository has data available, also have the tools available for user to use. This website, I'm going to give you the website at the end, and you could go and then take a look. Now, for now, it has a synthetic power grid models available, which you can download and use it. And then those models coming from different places, not just P&L. But moving forward, we will also think about using the similar technology to manage measurement data as well. So then it can be much more comprehensive to support any kind of user research and applications. So that's for that. Oh, here's the website. It's called the DR Power, and this, I guess, now I have I think close to hundreds or a couple hundreds of data sets available in this website. And then one last thing is about, again, data use. This is one effort, again, hosted by P&L. It's called a grid optimization competition. What it does is P&L is the host, which means we provide the software, hardware, and also the platform to receive the algorithms, particularly here it's OPF algorithms, and then we would run it and then compare and then make a rank list and then post on the website. And eventually, if anyone would win, coming to the top, there's a $4 million prize to be given by ARPA-E. And now ARPA-E has a funding call out requesting for proposals of developing such OPF algorithms. So I would encourage you to take a look and see whether you have interest. If you are having work in this domain in the OPF area, there might be a good opportunity to do some research as well as have a chance to win some prize. So with that, I would end here. I hopefully you have some questions and then we have some conversation. But just to quickly summarize, so really the power grid data issues become much more complex compared to old days. Have volume issues, speed issues, and then have a lot of information we could gain from the measurement, but the challenge is how we do it. And then there are efforts going on to address those challenges at the P&L and other places too. So some examples I gave, like a Gauss, multi-domain data reasoning, and also visualization, those can be part of the solution, but I think there's a lot more should be done. And here's the people I work with, and then made a lot of contribution to the things I talk about, and also the funding from different offices in DOE. Appreciate all the support by the programs. So with that, once again, give you those websites. Then I'm also welcome any questions.